Okay, so hello and welcome everyone to week 4 of interactive live sessions for the course on fluid dynamics and turbo machines. This course is being offered by NPTEL. It's being instructed by Professor Shamit Bakshi and Professor Dhiman Chatterjee from the Department of Mechanical Engineering at IIT Madras. My name is Debjit. I'm a PhD scholar at IIT Madras and I'll be the TA for this course. Like every other week, we shall be solving some problems together. So without any further ado, let's get started. So this week our discussions has been on differential analysis of fluid flows as well as viscous flows, and there are two specific cases, one being the flow over a flat plate leading to boundary layer, and we touched a little bit upon pipe flow, viscous flow through a pipe as well. So with all that, let us start. So the first question uh, is asking us that the Navier-Stokes equations reduce to the Euler equations for what conditions? Under what set of conditions? Is it option A, when high for high Reynolds number flows? Sorry. Okay. Alright. Sorry. So, question number 1 is asking us that the Navier-Stokes equations reduce to the Euler equations under what conditions? Is it option A, high Reynolds number flows? Is it option B, inviscid flows? Is it option C, compressible flows? Or is it option D, flows with velocity potential, meaning irrotational flows? So when does the Navier-Stokes equations reduce to Euler equations? Is it for option A, for high Reynolds number flows? Is it for option B, for inviscid flows? Is it for option C, compressible flows only? Or is it for option D, flows with velocity potential? Alright, so let's take a look at the solution. It's actually option B, inviscid flows. So under inviscid conditions, the Navier-Stokes equations boil down to the Euler's equation. So let's, you know, so we have seen how the Navier-Stokes equations look for uh, a Cartesian coordinate system in x and y. So if we use a different coordinate system instead of the traditional XYZ rectangular Cartesian coordinate system, let's say we have a streamline like this, and uh, so if we fix our coordinate system along the streamline, calling this the streamwise direction, and we write down the Navier-Stokes equations in the streamwise direction, then it can be written in a way like this. So, um, do s. So instead of x or y, it becomes do s. Sorry. First one is do t, that's the temporal term. Then we have the convective term, which can be written as u do s, where s is the uh, streamwise direction, this being equal to minus the gradient of p plus the viscous term. So, in the absence of uh, viscosity, this term goes to 0, and then whatever we are left with is nothing but the Euler's equation, where the total derivative of velocity or the acceleration is caused due to differences in pressure only. I'm sorry, there should be a 1 by rho over here minus 1 by rho dou p dou s. So it is in case of inviscid flows that Navier-Stokes equations can be reduced down into Euler's equations. Okay, let's move on to the next question. So question number 2 is asking us that in boundary layer theory, displacement thickness physically represents what? Is it option A, the actual thickness of the boundary layer? Is it option B, the distance by which the external streamline is displaced? Is it option C, the thickness required for zero velocity at the wall, or is it option D, the wall normal coordinate? So this is week 4 of interactive live sessions for the course on fluid dynamics and turbomachines. And like every other week, we are solving some problems together. This is question number 2 of today's session. That is asking us that in boundary layer theory, what does displacement thickness physically represent? Is it there are 4 options given below. So option A is that the actual thickness of the boundary layer. Option B is the distance by which the external streamline is displaced. Option C, the thickness required for zero velocity at the wall. Or is it option D, the wall normal coordinate? So read the question and the options carefully. Then once you can pick the correct option, you can either type in the chat box or you can unmute and answer, whichever way you feel comfortable. Okay, so let's take a look at the solution. It's actually option B, the distance by which the external streamline is displaced. So although displacement thickness is defined mathematically in this way, 0 to infinity 1 minus u over u infinity, which is this free stream velocity, into dy. Now, what this physically means is that, and let's call this delta star, where delta is the actual thickness of the boundary layer and which is not equal to the displacement thickness, nor does it physically represent it. So what this means is, this is also called the velocity deficit. So it's like if I forget about delta star thickness of fluid flowing near the wall, then the rest of the flow can be treated as it was in the absence of the boundary layer. What I mean by that is something like this. Let's say I have a flat plate and there is and uniform flow velocity coming in with, perfectly horizontal streamlines like this. Now, due to the boundary layer formation, what happens is that these streamlines, they get deflected by a little bit, right? Because the flow slows down due to the viscous effects near the wall. Now, if I can forget about this much thickness of the boundary layer, then this particular streamline, this got shifted over here. So that's the displacement in the streamline, and above this region it can be treated as simple inviscid flow. We don't have to worry about viscosity and boundary layer equations, the flow gradients, velocity gradients within the boundary layer. We do not have to consider in that region outside the uh, displacement thickness. We can just simply treat it as if there was a inviscid body which deflected the streamlines in a certain way and treat it as a simple inviscid flow. So that's what the displacement thickness physically represents. Okay, so let's move along. We'll move on to question number 3 now. It's match the following type of question. We have two options on the left hand side and two options on the right hand side, and we have to match them in a correct way. So the clue over here is that what is the critical Reynolds number, also written like this, Reynolds number CR, for each of these two cases. The cases being option A, flow over a flat plate, and case B being pipe flow. And there are certain numbers. These numbers are basically the critical Reynolds numbers for that particular flow regime. So the two numbers are 2300 and 5 into 10 power 5. So which one is the critical Reynolds number for that particular flow situation? And what does critical Reynolds number mean? It means that if your Reynolds number is less than Reynolds critical, then it always has to be a laminar flow. So whatever disturbances are introduced in that flow, they die down with time. They do not grow or sustain. So, any kind of uh, disturbance does not grow. It's perfect. The viscous effects dominate, and those disturbances die down, as a result of which we get laminar flow. So that is always guaranteed. Now, what happens if Reynolds number is greater than that? Then it may or may not shift from laminar flow. It's a common confusion that people think if the Reynolds number is above the critical one, it has to be turbulent flow. But that's not always the case. The transition from laminar may or may not begin in the presence of disturbances above the critical Reynolds number. So this really leads to, transition and growth of instabilities. Transition instabilities and may boil down to turbulence, but that's not guaranteed. But what is guaranteed is that, if it is lower than Reynolds critical, then it has to be laminar. Okay, so let's take a look at the solution. The solution is A2B1. So for flow over a flat plate, the critical Reynolds number is 5 into 10 power 5. That's quite a high number, but we have to keep in mind the way in which Reynolds number is uh, determined in this case, Rex being rho ux along the streamwise direction divided by viscosity mu. And for pipe flow, this number is 2300, and in this case, Reynolds number, the length scale for Reynolds number is the diameter of the pipe. Rho ud, diameter of the pipe, divided by mu. And that number is 2300. So this actually comes from the famous experiment by Osborne Reynolds, where he showed that uh, you know below a certain critical Reynolds number, the flow remains laminar, and above that, the perfect laminar flow starts breaking down, and you get ripples in the uh, streak that he was injecting into the flow. There is a lot of theory which goes behind this. Things like the linear stability analysis and or Sommerfeld equations and all that. So there are theoretical backgrounds for many different, simple canonical flow situations where you can predict the critical Reynolds number above which instabilities may or may grow, below which they always die down. Alright, so let's move on. We'll move on to question number 4 now, which is asking us that the ratio of maximum velocity to the average velocity for laminar flow in a circular pipe is given by what? Is it option A 1, option B 2, option C 0.5, or is it option D 0.25? So for flow through a circular pipe, we know that it's parabolic in nature. This could be X, this could be R, and what I'm looking for is the ratio of the maximum velocity U max over the average velocity equals what? Is it option A1? Is it option B2? Is it option C 0.5? Or is it option D 0.25? So what is the ratio of maximum velocity to the average velocity for laminar flow in a circular pipe? For laminar flow in a circular pipe, is it option A1? Is it option B2? Is it option C 0.5? Or is it option D 0.25? Let's take a look at the solution. It's actually 2. So, let's try to solve this. So, we know that u by u infinity or sorry, u by u average for uh, for laminar flow through a circular pipe is given by 1 minus y square by r square, sorry, r, right, r square, r being the radial direction, by capital R square, where r is the radius of the pipe, the inner radius of the pipe, right? So, for u max, this is equal to u max at r equal to 0. So, u is equal to u max at r equals 0. That is at the center of the pipe, because this is a parabolic profile. The maximum is at the center. So if I plug this into this equation, we get u max over u average. So instead of r, we'll put 0. So it will be 1 minus 0. Sorry, this is not u average. This should be u max instead. We need to find out what u average is. So u average, let's integrate from 0 to capital R of whatever u there is multiplied by the area through which it flows, so 2 pi r dr, and we have to divide this by the total area of the pipe, which is 1 by pi r square. So let's evaluate this. We have 1 by pi r square outside, and let's take things out from here. So 2 pi is a constant which I will take out here, and we have to integrate from 0 to r. We have u r dr. Now u I'll replace by this formula here, and there will be a u max is also a constant which I am taking outside the integral, and RdR. So pi and pi cancels out. We have 2 u max over r squared outside. And let's evaluate this integral. So, if I multiply r, then this uh, term within the integral, this becomes r minus r cube by capital R squared. And if I integrate with respect to dr, what do I get? I get r squared by 2 minus r power 4 by 4 capital R squared, and this goes from 0 to R. So at 0, this is 0. I can just replace the small r squared by capital R squared. So I'll just write capital R square here and capital R power 4 here, and I'll evaluate this. So this is R square cancels out, I have R square remaining, and this R square we can take common outside. So we have 2 u max by r square. 1 r square came out from within the brackets, and inside the bracket I have half minus 1/4, which is equal to 1/4. And I can cancel the 2 out, the r square cancels out, and the left hand side all along has been u average. So this. I'll move over here for the lack of space. So, what we got here is that u average is equal to u max by 2. And what we need is the ratio of the u max to u average. So if I now write u max by u average, then that should be equal to 2. And this is true for any laminar flow through a circular pipe. Hence, option B is the correct one. Alright, so let's move along. We'll move on to the next question. We'll move on to the next question. That's question number 5, which is asking us that water with a kinematic viscosity of 1 multiplied by 10 power minus 6 meters square per second, and density 1000 kg per meter cube, flows through a horizontal pipe of length 100 meter and diameter 0.05 meter at a flow rate of 6 into 10 power 5 meter cube per second. That's the flow rate. So there are two things we have to calculate. We have to calculate A, the Reynolds number, and option B, the pressure drop between the two ends, assuming fully developed laminar flow. Okay, so first of all, let's find out what the Reynolds number is. So the formula for Reynolds number for a pipe of diameter d is given by rho u d by mu. Now mu by rho, that is nu, so we know that nu is given and d is also given, that's this 0.05. We don't know u, but we do know the flow rate and the diameter of the pipe, so we can calculate that. So u is basically the average u, that is equal to the flow rate Q divided by the area, which is pi d square by 4. So let's evaluate this. 4 into flow rate, which is 6 into 10 power minus 5. And this has to be divided by pi into d square. D is 0.05, so 0.05 squared. I'll take the help of my calculator here to evaluate what this is. So, yeah. So we have 4 multiplied by 6 multiplied by 10 power minus 5. Then we need to divide this by pi, and we also have to divide this by 0.05 square. So what we get ultimately is 0.03 something. So I'll just keep 0.03 meters per second being the velocity. So let's calculate the Reynolds number now. We have 0.03 into diameter, that is 0.05, and the viscosity, which is 10 power minus 6. So basically we can remove these two decimals and multiply by 100 So this is 3 into 5, 15 into 100, that is 1500. So basically, since this is less than the critical Reynolds number of 2300, we can say that the flow is laminar flow. Although it's given in the question, it's a good way to check. Okay. Now, the second question is the pressure drop. Now, we know the pressure drop for laminar flow through a circular pipe P is given by 32 mu dl, where L is the length of the pipe, divided by d square. Sorry, this has to be U by d square. Right? Da, da, da. Yeah. So 32 into, okay, mu we need to find out, that is simply rho into nu. So we can write 1000 into 10 power minus 6. That's our mu. Into u we found out as 0.03. The L is given as 100 meters. And we have to divide this by the diameter squared, so 0.05 square. Let's see. So let's simplify this first a little bit. So 100 into 0.03, I can simply remove this decimal. We just have 3 over here. And 1000 into 10 power minus 6, we can write as 10 power minus 3. And down here, I can call this as 5 squared into 10 power minus 4, which if it goes up, it becomes 10 power 4, and I can multiply these two and get a 10. So what I have is 32 into 10 into 3 divided by 25. This should be pretty straightforward to calculate. So I have 32 multiplied by 30 divided by 25. So it's around 38.4. So 38.4 pascals. That's the pressure drop across the pipe given that there's a fully developed laminar flow flowing through it, also known as Hagen-Poiseuille flow, or the Hagen-Poiseuille solution to flow through a circular pipe. Alright, so let's move on. We move on to question number 6 now. So now we are starting to talk about flow over a flat plate and boundary layer flow over a flat plate. So the Blasius solution is one of the most crucial solutions to the boundary layer, and the Blasius equation is a similarity solution. So these are things we went through in the lectures. So what is a similarity solution and how to find one? And so this question is asking us that the Blasius equation is a similarity solution of the boundary layer equations for what? Is it for option A, for flow over a sphere, for B, flow inside a pipe, is C for flow past a flat plate, or is it option D for flow in a free jet? It's a very simple solution, and I guess I already told you the answer. So, without any further ado, let's take a look at the solution. It's actually flow over a flat plate. So, whenever a free stream comes and hits a flat plate in its streamwise direction, then a boundary layer is formed. Boundary layer meaning a region in space within which the effects of the boundary is felt, and that is felt only for viscous fluids. This is through the act of viscosity. So we get, instead of a continuous uniform velocity profile which was coming in, we get sort of an increasing velocity profile, or velocity gradients get set up within the boundary layer, and finding this velocity profile is very crucial, especially for understanding what is the shear stress, as well as in case of heat transfer, what is the temperature gradient, and that dictates the rate of heat transfer between the solid plate and the fluid flowing over it. So anyway, so in order to know the gradients, we need to know what the velocity profile or the temperature profile actually is. And it was Blasius who first, gave a very elegant solution to this problem, and that's known as the Blasius solution or the Blasius equation. And it is a similarity solution which was applied for boundary layer equations for flow over a flat plate. Okay, so let's move on. We'll move on to question number 7 now. So, according to the Blasius solution for a flat plate, the thickness of the laminar boundary layer delta at any distance x from the leading edge varies as what? So, if this is the boundary layer, and let's say this is where my coordinate system starts, this being x and this being y, and the boundary layer thickness at any given x being delta, it's a function of x. So, and this point over here, this is known as the leading edge, the edge that faces the flow. What is, so how does the boundary layer vary along the uh, streamwise direction x? Is it option A, nu x u infinity, nu x over u infinity power half? Here, once again, nu is the kinematic viscosity and u infinity is the uniform free stream velocity that comes and hits this flat plate. So is it nu x over u infinity power half? Is it option B, nu x over u infinity power 1/3? Is it nu x over u infinity power 1/4? Or is it nu x over u infinity power 1/5? Okay, so let's take a look at the solution. It's actually option A. Let's see how we get there. So one easy way to remember one of the key uh, findings of the Blazier solution is that delta over x is goes as 5 over root Reynolds number x. Rex. Reynolds number defined by the uh, distance from the leading edge. Now, uh, in order to find the x y's variation of delta, we need to send this x over there, so it becomes 5x. And let's break down Reynolds number. It can be written as uh, u infinity x over nu. So there's a x in the numerator and there's a root x in the denominator. So if we simplify this, so it can be written as 5 remains as it is. We have 1 comes up, new power half comes up in the top. We have u infinity over here, and we have x, and this whole thing is power half. So x power 1 minus half becomes x power half. There's a nu over here which can be written in the numerator, and u infinity stays as it is. So this is the formula for delta. And if we can forget, 5 is sort of the proportionality constant there. It's not exactly 5, it's a number which is very near 5. We can for the sake of uh, remembering it, we can call it 5. So basically, the functional dependence of delta goes as the nu x over u infinity power half. So option A should be the correct answer. Alright, so let's move along. We'll move on to question number 8 after this session, which is asking us that for the glaciers boundary layer, once again, what is the wall shear stress at x? Is it option A 0? Is it option B nu dou u dou y at y equals 0? Is it option C rho u infinity squared? Or is it option D 2 mu by u infinity? What is the wall shear stress? Also, it's represented as tau w, tau wall at x. Okay, let's take a look at the solution. It's actually option B, pretty straightforward. So this is nothing but, Newton's law of viscosity, nothing special about boundary layers here. So if this is my coordinate system x and y, and flow comes in and there's a boundary layer set up, and there's this velocity profile like this being u as a function of y, then shear stress depends on this gradient over here. This gradient is dou u dou y over where at y equals 0. This is the gradient, and the viscous or the wall shear stress would be nu into this velocity gradient over here. So dou u dou y at y equals 0. So this whole thing again is a function of x. So this will vary at different points in x. Okay. Alright, so we got done with question number 8 of today's session. Let's move along to question number 9. Once again, in the Blaze's solution, the wall shear stress varies as what? Is it option A, x power half? Is it option B, x power minus half? Is it option C, x squared? Is it option D, independent of x? Meaning it doesn't, it's not a function of x.